In the last episode, we ingested support documents, chunked them, embedded them, stored them in the Postgres with the PG vector. Now we build the retrieval layer that finds the right chunks when the user asks the question. I will show the results first, and then we walk through the 5 retrieval models that make it work. So we have chunks in the database from episode 2. I send a post request to a retrieve endpoint with the query how do I reset my password and ask for a top 3 results. The endpoint returns 3 chunks. Each has an ID, source file, chunk index, the text itself, and the final score. The top chunks is from the frequently asked question and contains the exact password reset instruction. Notice that second chunk also mentioned account recovery. The vector search caught the semantic connection even though it doesn't use the word reset. That is hybrid retrieval working. 2 search methods, 1 ranked result. Now let us walk through the code that builds all of this. We start with typespy, which defines scored chunk, a data class that carries a chunk through a retrieval pipeline. It has the core fields from the database, which are ID, document ID, source file name, chunk index, and text. The metadata field is a dictionary that holds access control rules. Then we have 4 score fields. The score field is the final ranking score that changes at each pipeline stage. Vector score holds the cosine similarity from vector search, and keyword score holds the term frequency rank from full text search. RRF score holds the reciprocal rank fusion score after the merge the 2 lists. As chunks move through keyword search, vector search, fusion, and rerank, we update the relevant score fields so we can see which signal contributes what. The keyword search function runs Postgres full text search over the TS vector column we set up in the second video. The query uses the plain to TS query to convert the user question into stamped search terms. Then the double-8 operator filters chunks where the TS vector matches those terms. We rank results with TS rank CD, which scores chunks by term frequency and document length. The function returns up to 20 candidates as scored chunk objects with keyword score set to the rank value. If the query is empty or no chunks match, we return an empty list. This is the sparse retrieval side where no equal handles words variations like reset, match, resetting. So exact keyword overlap is more flexible than string matching. The vector search function runs nearest neighbor search using the pgvector cosine distance operator we set up in episode 2. We pass in a query embedding a 1536-dimensional float vector from OpenAI. The SQL uses this rocket operator which computes cosine distance between the query vector and each chunk embedding. We convert distance to a similarity score by subtracting from 1, so a score of 1 means identical and 0 means orthogonal. The query orders by distance ascending and limits to 20 candidates. We register the pgvector adapter is in episode 2, so psyhook.py can serialize the query embedding. Each result becomes a scored chunk with vector score set. This is the dense retrieval side. It catches paraphrases and synonyms that keyword search misses, like matching forgot credentials to password reset based on semantic meaning rather than exact words. The reciprocal rank fusion functions merges the keyword and vector ranked lists into one fused list. RRF is a ranked-based fusion method. For each chunk that appears in any list, we assume 1 divided by k plus rank across all lists. The default k is 60, a standard constant from information retrieval research that balanced top-ranked precision with broader coverage. We built a dictionary keyed by chunk ID to accumulate scores, then sort by RRF descending. The function preserves both vector score and keyword score on each chunk, so the rerank step can use them both. RRF works because it ignores row score magnitudes. Keyword scores and vector scores have different scales, but ranks are comparable. When both methods agree, the RRF score doubles, signaling that both retrieval paths found the chunk relevant. The rerank chunks function applies a lightweight second pass rerank over the fused candidates. We normalize the vector scores and keyword scores to 0 to 1 range by dividing each by the max in the candidate set, necessary because keyword scores can range from 0.01 to 10, while vector scores are already cosine similarities in 0 to 1. Once normalized, we combine them with weights. 70% vector, 30% keyword, plus 1% RRF as a small tiebreaker. The 70-30 split prioritizes semantic match while preserving exact term signals. These weights are placeholder heuristics. Production systems tune them by testing different combinations against labeled examples. We will cover evaluation in the later episode. We update the score field on each chunk with the weighted combination, and then sort them descending. This rerank runs only on the fused candidates, usually 20 chunks, so it is cheap. The retrieve function in pipeline py orchestrates the full retrieval flow. It takes a query string, a top k limit, and a user row. First, we run migrations to ensure the schema is current. Then we call keyword search and vector search in sequence. They could run in parallel, but for this episode we keep it simple. We embed the query using the same OpenAI model we used for the ingestion. After fusion, we call filter by role, which checks the metadata allowed roles list on each chunk against the user role and removes chunks the user cannot see. That access control filtering happens after fusion, so RRF scores are computed on the full candidate set. Finally, we slice the top k results and return the retrieve results data class with the query and the ranked chunk list. The function accepts an embed fn parameter for dependency injection, so we can mock embeddings and tests without calling OpenAI API. The full pipeline, keyword search, vector search, fusion, ACL filter, rerank, runs in under 50 milliseconds for 20 candidates on the table with 10,000 chunks. The pipeline is stateless, so no session, no catch, just query in, chunks out. And that makes it easy to scale horizontally when traffic grows. The fast API route is in API routes retrieve py. It accepts a post request with a retrieve request body that is the pydantic model with the query, top k, and user role fields. The route calls enforce or block with the placeholder for prompt injection detection. In this episode, it always returns none, so no blocking happens. When we call the retrieve function from the pipeline, passing the query, top k, user role, and settings. The result is a retrieve result with scored chunks. We map those to retrieve chunk pydantic models, which drop the internal score fields like vector score and keyword score and keep only the final score. The response is the retrieve response with the query and the chunk list. The route is registered in the main py, so it is available at retrieve endpoint when the fast API app starts. The settings class is config.py, holds retrieval parameters. Retrieve top k defaults to 5, that is how many chunks we return. Retrieve candidate limit defaults to 20, that is how many candidates we fetch from each search, mentioned before fusion. Larger candidate pools improve recall at the cost of rerank latency, but 20 is a good balance for the tables under the 10,000 chunks. RRF k defaults to 60, the standard RRF constant. We built a hybrid retrieval with 5 models that take a support question and return the most relevant chunks with scores. The retrieve endpoint is alive, keyword search catches exact terminology, vector search catches paraphrases, and Fusion ranks them together. The retrieval layer we built today is the foundation that makes grounded answers possible. As the series continues, we will add the generation layer, prompt construction, LLM call, and answer generation with citation, grounded in these retrieved chunks. If you found this video helpful, learned something new, or discovered ways to simplify your workflow, boost your productivity, or even save money, please subscribe my channel and hit the like, because it really helps me to grow and keep digging to discover new things and continue creating more content like this. Also, leave a comment below with your thoughts, questions and experiences. My goal is for us to learn, grow and build real AI expertise together, and your feedback is an important part of that. Thanks for watching and see you in the next videos. Laughing, dance all night.